Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome ILYA Shapiro. I think this is your first time as a speaker at our seminar. And it's cyclic homology, coefficients and limits, a topic very dear to my heart because this is cyclic homology. ILYA, take it away.
Thank you very much for the invitation. And well, yes, let's begin. Let's begin with the title. So we have cyclic homology, which of course, classically cyclic homology of associative algebra, originally due to Alan Cohn and other people. And the coefficients arose initially in the equivariant setting. So when you have an algebra that have an action of a Hopf algebra, then it turns out that if you want to compute its cyclic homology and not forget about the action, then you need special objects, which are, of course, stable anti-Eddy-Drinfeld modules introduced by Piotr and other people. And limits, of course, go back to, the definition of categories, and I guess due to MacLane and others. So the idea is to use limits to think about coefficients, help us define them, and see what they are. So some of this stuff can be found in Hopf cyclical homology and beyond, which was a joint paper with Masood, published in Proceedings of Symposium Pure Mathematics. In fact, just today I got the book. It's quite thick. So that's the introduction. So the setup is as follows. We have a ground field over which everything is defined, and it's not that maybe it's necessarily algebraic closed of characteristic zero, but that's what I was thinking about. So let's just fix that.
I mean, some of reformulations of cyclic homology require it. If you remember, papers of Lodek-Quillen, and they have their standard by now description, double complex, blah blah blah.
Yeah, sure, but you see, once things are general enough, I suppose anything goes.
Okay.
Right? But after, you see, my idea about this talk is not to dazzle you with wonderful generalities, but to actually make it boil down to your description. Modules, comodules, and relations. That is something you can feel with your hands.
Yeah, it's tangible.
It's tangible. Whereas you can say very beautiful words that mean nothing to most people, then it's not so tangible. Okay, so let's just say algebraically closed of characteristic zero, which probably means that you can get something nice and tangible. But again, the definitions probably don't need it.
Yeah.
So my algebras, when I say algebra, I mean unital associative, and they live in monoidal categories. So monoidal category is a category where you can multiply objects, and you need to be able to multiply objects in order to define an algebra. Otherwise, you can't say what an algebra is. Okay, and bialgebras. So I will have two main examples: bialgebras, which I will discuss briefly, and mostly I'll be describing Hopf algebras and braided categories. So the bialgebras live in vector spaces. So the category of vector spaces, which is symmetric monoidal. So it's monoidal, and you can interchange objects up to isomorphism, right? And isomorphism, if you do it twice, you get back the original thing. So we'll get back to that when we talk about braided. But the point is, in principle, to define bialgebras, you need some sort of a braiding in your category. You need the ability to say that x times y is the same as y times x. Otherwise, you can't even define a bialgebra, because bialgebras, you need multiplication, co-multiplication, and a compatibility between them. And to express the compatibility, you need some sort of braiding. Strictly speaking, not true. Some sort of a duoidal category will do, but something like braiding. And then a Hopf algebra H. So whenever you see H, if I forget to say it is a Hopf algebra, it lives not in vector spaces, because that would be boring. Although I think it will be the beginning of the story. It lives in the rigid braided category. So braided category, again, is a monoidal category where x tensor y is identified with y tensor x in perhaps a non-trivial manner. And furthermore, if you do it twice, you do not get the identity map. When you do get the identity map, it's called symmetric. That's vector spaces, for example. But symmetric is also not super interesting. It is. The reason why I like non-symmetric is because then there are fewer choices. When things are simple, there's too much choice. things become same and you're not sure what to do. So if they're not symmetric, then there is usually only one choice. So that makes things actually easier.
So you like symmetry breaking.
Yes, yes. Well, I mean, there are a lot of fun things like that. We might talk about it later, but the point is that, of course, whatever I say about the braided category is true about the symmetric category. It's just that if you don't assume symmetry, things are actually clearer.
And can you remind me what the rigid stands for?
Oh yeah, rigid. Yes, I actually want to talk about rigid because it's also very interesting. Rigid means you have duals. You have duals. Now, rigid, I always thought has to do with finite dimensional, right? Like in vector spaces, if they're infinite dimensional, you don't have duals. And I mean, of course, you do, but not the duals that are the rigid ones, you know, like a double dual should be somehow related to itself. Okay, and you don't. So I always thought it's a matter of finite dimensional, but it isn't. It isn't. It's more of having inverses. So, for example, if you have bialgebras and you consider their monoidal category of representations, that is not going to be rigid, finite dimensional or not. Whereas if you have a Hopf algebra, then you have the antipode, which is kind of like inverses, and it will be rigid. So rigidity in an essential sense has to do with inverses, not with finite dimensionality. Even though strictly speaking, yes, you need finite dimensional, but that is somehow an inessential distinction. The essential distinction is the inverses. And that I will talk maybe a bit about that when I talk about bialgebras. And to simplify things, of course, anti-Yeta-Drinfeld modules were the original coefficients. They were followed fairly soon by contramodules, which in general are related but different, and there are relations between them, and there are complications, and you really need one versus the other if H is infinite dimensional, but when H is finite dimensional, there is no difference. I mean, they are identified. So there is no point worrying about it. Let's just assume H is finite dimensional because things are nicer and it's still interesting. Okay, and
by the way, if you don't mind me just jumping in, because otherwise
no, I do not
forget.
mind. I do not mind. I do not mind.
You see, we were wondering, because you said, okay, when H is finite dimensional, then even though contra modules are different animals than modules, if H is finite dimensional, they are identifiable. So we're wondering about the same possibility for anti-Drinfeld modules versus Yeta-Drinfeld modules. We know that they are by design different creatures. One is like an affine space, one is like a vector space, but still they are identifiable for many Hopf algebras. Any Hopf algebra admitting a module pending involution allows you to identify Yeta-Drinfeld and anti-Drinfeld. But, and it was a very difficult thing. I think somebody did a PhD in Germany on this topic.
I'm aware, yes.
The problem that indeed there exists finite dimensional Hopf algebras which do not admit modular pairs in involution, which means one-dimensional anti-Drinfeld modules, which means you cannot identify anti-Drinfeld and Yeta-Drinfeld even though you are finite dimensional. It's just a remark, but I think it's very interesting.
You know what else is very interesting? That if you go to bialgebras, there is absolutely no relation between Yeta-Drinfeld and anti-Yeta-Drinfeld when correctly defined. You don't have to look to some pathological examples. You don't have to work very hard. There is absolutely no link between them. It's just everything breaks down once you drop rigidity. But again, this is something else.
Okay, it's good to know. I didn't know it. Okay.
And actually, I will talk about the relationship between Yeta-Drinfeld and anti-Yeta-Drinfeld modules. In particular, I will talk about the monoidal structure. So we will come to that.
Okay.
It's also very interesting. Everything is very interesting. So much interesting stuff going on. So the note is about the categorification. So the idea is this. It's quite quite nice. You have an algebra in a monoidal category. You want it cyclic cohomology. You need an object which is a coefficient. Without it, you cannot do anything, right? It turns out that these objects come from the cyclic homology of the monoidal category. Now, monoidal category is like an algebra, right? You can multiply stuff. So it's a categorification of a notion of an algebra. So it also has cyclic homology, and cyclic homology of monoidal category yields the coefficients for the theory for algebras in the monoidal category. So you see, it's all very much related. So in what I'm doing is I'm going from algebras to monoidal categories, and we will see in the first few slides how we just take what we do for algebras and we do it for monoidal categories, and that will be our coefficients. And that is not the same as replacing algebras by categories. And so you can do both, but then you get two categories, and two categories are nice, and they play a role in this story, but not in what I will be talking about today. So for us, we just go from algebras to monoidal categories because, you know, monoidal categories are like algebras. In fact, to do it completely correctly, you would have to go to like all the way up to infinity categories, but we won't do that. So the motivation for this is that you have, you know, cyclic homology of an algebra in a monoidal category only if you have coefficients. And for example, a monoidal category that the story begins with is representations of a Hopf algebra, right? If you have a Hopf algebra, then you have a monoidal category. In fact, the bialgebra will do for this, but it won't be as nice of a category. And it needs coefficients, and of course, these are the anti-Drinfeld modules of Piotr and his co-authors, stable ones. And well, we want to study coefficients themselves. Why are they interesting? Because in a very real sense, a very precise sense, they are analogs of D modules. So these are like, you know, generalizations of vector bundles with connections. So nobody would argue that the vector bundles with connection are interesting. So it is not true that you might want one coefficient or two coefficients, you know, in modular pair involution in your set. No, you want to understand them all. Just like you want, if you have a space, you want to understand the category of D modules on it, and it tells you a lot about the space, and they come up in like representation, geometric representation theory. Similarly, you want to understand all coefficients, not just, you know, one or two. So we wanna really understand coefficients, and for that, especially if you vary the setting. Of course, if you want to understand coefficients and your category is representations of a Hopf algebra, then there's nothing I need to do. That's been done, and it's it's modules, comodules over H, and a compatibility condition, and those are your anti-Drinfeld modules. But in general, it's not that easy. Like, of course, they exist. Right? People have looked at things and they decided that these are the anti-Drinfeld modules, and quite often they're right. Other times I would argue they're not right. But in any case, my understanding is the approach was always to try to generalize this definition of H modules and H comodules and do whatever else you need. But if you had a reasonable abstract definition to apply anywhere, and of course this definition, if you just want to wave your hands maximally, is just take the cyclic homology of the monoidal category, and that would be your definition. So your definition of coefficients is the cyclic homology of the monoidal category where you're looking for your algebras. And that's perfectly fine abstract definition. Of course, saying it like that doesn't help you understand it at all, but it's something. So we don't have, it's not enough to have an abstract definition. We want something computable. And by computable, we really mean like, you know, H action, H coaction, and a compatibility condition, because that is as computable as I suppose it can be. Okay, so that is our goal. Oops, skipped too much.
Sorry, Ilya, could it be that computable means also homotopy invariant?
You see, you are using big words, right? No, it's the opposite. We want small words. We want computable to us means that anybody could do it. Like you can teach like maybe an undergraduate to figure it out. You just say, here's the algorithm, and you go ahead and you compute it, and he should be able to do it, or she.
I mean, typically, like computable, I mean, this, if it's something derived functor, is considered computable. I mean,
okay, I think I see what you're saying. I think
yeah,
in your sense, computable is completely opposite of what I would mean by computable. So analogy would be singular homology versus something like cell homology, right?
I see, yeah.
I would call cell homology computable, and you would call singular homology computable, because an undergraduate could compute, cellular decomposition and just write it just all very finite, a few maps,
Okay.
I can do it by hand. Whereas if you have singular, it is so invariant and so wonderful and has fantastic properties. So you can usually compute things without getting your hands dirty, and you would call that computable.
Mhm.
So no. My computable is in the simple-minded sense of cell homology.
I see.
Like
Okay.
I actually want action, coaction, and compatibility conditions.
Some explicit complex. Yeah.
To define the coefficients, there is no complex after everything is done. It is exactly analogous to H modules, H comodules, and compatibility conditions. Of course, if you want to compute cohomology after that, then I will show you a recipe on the last page, and there, yes, you will get a complex.
Okay. Very good. Yeah. Thank you. Yeah.
Yeah, no problem. But the whole talk, except for the last page, is just looking at the coefficients. It's like we just forget about how to actually compute homology of an algebra with those coefficients. We just want to study the coefficients.
Okay. Very good.
Okay, and so a quick review of cyclic homology is that if you have an algebra in vector spaces, so what you do is you just do the following thing. You take tensor powers of A, indexed by natural numbers and 0, and then you define operators which encode the product, and these are the faces, and then there are degeneracies which encode the unit insertion, and that would be just well, even that is not enough for a simplex category, but definitely if you want the cyclic one, you want this cyclic relation, right? You want to be able to take a string and move the end of the string to the front. And that actually figures into one of the phases as well. It's not restricted just to the cyclic category. So we have a simplex category denoted so, and the Cohn's cyclic category denoted so. And the above operators can be summed up as being A given a functor from lambda to the vector spaces, right? These are the values on all of the elements, and all these maps give you the necessary maps between the resulting vector spaces. And then once you form that functor, you can take a limit. So here are the limits from the title. You can take a limit of this diagram, and of course you should do it in a derived sense in order for you to really recover Hochschild homology or cyclic homology. So this will be a recurring theme. If we take a limit only over part of the structure, we get Hochschild homology. If you take the limit over the whole structure, you get the cyclic homology. And we'll see that if you take the limit partially, the remaining structure that you haven't utilized in taking the limit is visible in a sort of this operation, extra operation that you have left. Okay, so let us talk about diagrams of categories. So before we had diagrams in the usual sense, where we have a fixed category and we have a functor from some small index category to that category. Here we have an index category, and we have an assignment to every element of the index category of a category, not an object, but of a category. And then, of course, for every homomorphism in the index category, we must have a functor between the corresponding categories. And we have, of course, these isomorphisms, which is data, right? This is extra data. These aren't just that they're isomorphic. These isomorphisms are given, and they must satisfy certain compatibility conditions. I mean, there is nothing here. It's just if you try to write down what you need, that's what you need. And then there is, for every category, we can have a trivial diagram where it assigns to every index object that fixed category, and every morphism gets assigned the identity functor from T to itself. And of course, all of these associators are identity, and everything is trivial. The point is that the limit is simply the left adjoint to this constant diagram functor.
And can you remind me what I is? This is what the directed set. What is I?
I for us will be either delta, the simplex category,
Okay.
or lambda, the Cohn cyclic category.
Okay, so
It
it's
is
a category.
It's an category is there are different flavors of categories. It's kind of a smallish category. Well, actually a small category, where objects form a set. Right? Yeah. Not a category like a vector spaces category. That's not a set.
Okay.
So it's some sort of it's a diagram, you can picture it, points and arrows between them, and there aren't too many of them.
Yeah, because take a limit over I, so this is why I ask if it's a directed set.
It's a category. It's a category.
But small.
Small. Very, very reasonable.
Okay. Okay.
You can touch it.
Okay.
So a section is a useful notion because we actually use it twice. A section of a diagram is a choice. In every category, you choose an object. And then whenever you have a map, you have this homomorphism of this sort, satisfying natural associativity conditions and compatibility conditions between the iotas that define this structure and this beta. Now, there are actually two flavors of section. This is a weak one, where this is just a homomorphism. There's also a notion of a strong section. That's when this is an isomorphism. So we need the weak one and we need the strong one, both. Although I think in the talk, only the weak one appears explicitly. So
we
this is
usually say Cartesian section in category theory if it's isomorphism. That's strong, but Cartesian section.
Sure. If you would prefer to call it Cartesian section, okay. So far this is I'm just showing you like what's involved, but I'm really interested in getting to concrete and explicit things. So once we get to that, then everything will be clear. But if something is not clear here, I wouldn't worry about it. But sure, if you want to call it Cartesian section, let us call it Cartesian section. So an arbitrary section of a diagram yields an object in the limit. So that's just an observation. And so if you wanted, you could just stop after the slide and say you're done. But that of course would be wrong. So if you have a monoidal category, which has some sort of an associative product, and you form a diagram over this as follows, just like for an algebra, except the monoidal product replaces the algebra product. And an A in C in an algebra yields a section of your diagram. And then you say, well, okay, you could do this Hochschild. You don't have to do cyclic. You just have to replace lambda here by delta. Then this is the cyclic homology. And A yields an element in here because a section yields an element of the limit. And then given a coefficient, which is just another element here, you can define the cyclic cohomology of A with coefficients in M as a home from this object that you got from the section and an arbitrary coefficient. So then you can say, okay, I'm done. And again, you should do this correctly. It should be derived and everything. And then you would truly recover cohomology with coefficients. If you believe that if you fix, and this is true, that if you fix your C to be representations of a Hopf algebra, then you will recover from this stable anti-Eda Greenfield modules. Actually, you will get counter modules. But of course, if H is finite dimensional, you don't care modules then. And then this would be the usual cohomology with coefficients and a stable anti-Eda Greenfield countermodule.
Sorry, this notation CH stands for?
Oh, it's I'd like to call it Chern character.
Chern character, okay.
So CH, it's just, as far as you're concerned, it's just notation. It's just A yielded a section of a diagram, and so in the limit it yielded an object. Okay. All of this is just beautiful words that mean nothing, but in the end everything will be explicit. So what do we have here? Okay, now we have a concrete description, right? Already we're passing from this not very descriptive definition to something more descriptive. We first thing we do is we change from the original functors to the right adjoints. Why? Because the direct limit gets replaced by inverse limit. So the co-limit gets replaced by a limit. Why? Because that is those Cartesian sections, you know, they're the ones I called strong sections. Those will just be Cartesian sections of the diagram, and those are much more understandable. Because that just means you have to choose an element in every single category such that there's these isomorphisms between the object already sitting there and the one brought over from somewhere else. And in the case of lambda, all it is it can be described very compactly. So it consists of a single object in the category, but it also is equipped with an isomorphism in here. So in a kind of a, I won't go into what this is, but you can think about it as if our C is modules over H, then this object here is modules over H squared. So an algebra which, you know, is H tensor H. So very concrete. And so we have a single bit of structure, right? There is usual structure and it has to have certain properties. Well, the structure is just an isomorphism between this and this. And in a moment, it will become more explicit what these are, because these look like, oh yeah, those were the faces, right? There were only two, and there is an isomorphism between them. But what are they exactly? Well, in a moment, we will see. And then there is the unit condition, that when you apply the degeneracy to this thing, you get identity on them. And then with the associativity condition, which is this. By the way, they're only called that because that's what they are in, say, modules of our Hopf algebra. They don't necessarily mean, you know, associativity and unit and stuff like that, as we will see in a moment. So the last condition, which is the stability condition, which is, if you were just keeping track of what's going on, if you are talking about anti-additional modules, the stability condition is the one that tells you that it's stable. So there's a certain map on an anti-additional module, and if it's identity, you call it stable, and if it's not, well, then it's not. And that is this that comes from this general condition when you apply to the case where C is H modules. And it can be omitted, and then you just get Hochschild homology, but it's still there. And so we see the sigma. This sigma will be with us for a while, and basically it pays to not so much consider the stable anti-additional modules. You should instead consider anti-additional modules and keep track of sigma. So this special thing where every element has this automorphism, and it might be identity, it might not be. So you have this special element left over because you're not considering HC, you're considering HH. So this is a very important element that we'll just keep track of. So this is a concrete description in general, but this is still okay in general, right? But then, suppose we want to go further towards anti-additional modules, because so far that wasn't what we had. Although,
Ilya, I have a question. So C, just remind me, is it just a monoidal category?
yes.
Okay.
C is just a monoidal category, although, I mean, like I said, the right adjoints, who said they exist, right?
Right. So this does not apply to category of algebras, for example. It's not monoidal.
No.
Not monoidal. Yeah.
No, the starting point for this is a monoidal category.
Yeah.
Right. If you have category of algebras, then what are algebras in there, right? The story is always the same. You have a monoidal category, you have algebras in there, you want to know what is their cyclic or homology, you need coefficients. What are coefficients? Coefficients are the cyclic homology of the monoidal category.
Yeah, that's clear. Yeah, thank you. Yeah.
No problem. And so if you have some sort of other category, then you have to do something else. Depending on the situation. Like the funny thing is that you can say these very general things and you think that it's done, but it really isn't done. It just there's always some twist. Anybody asks you a question and you think, oh, this question should fall under the general framework, and it never does. It's just somehow you still have to work to get it in there. So perhaps what you ask can also be with work shoved in here, but directly no.
Yeah.
Okay, so we have now this. We just look at the structure, which you see, this is what I promised. The tau was between delta 0 and delta 1, but really explicitly it's between this and this. What are these? This, of course, is the right adjoint to monoidal multiplication. So monoidal multiplication goes to C squared to C, and its right adjoint, of course, goes from C to C squared. So this sends M, which is in C, to something in C squared, which is the right adjoint to multiplication. And this is right adjoint to multiplication followed by a flip, right? So you just you flip it. Whenever you have two H actions, you can flip the two H actions, and now you have a different object over H squared. So a different module over H tensor H after you flipped it. So that's what I mean. So there's an isomorphism between the original HH module and flipped one, as long as that HH module came from a single M via this construction. And this is the structure, and the rest of the properties are properties. So now is a question of how to best interpret them. And so if you do the following, you take this functor instead. Notice that this functor goes from C to C itself, and then tau is encoded into this, which looks very much like an action, right? And therefore it's called act. So if you apply this to M and have a map from this applied to M itself, then via adjunction, just moving stuff around the way things are, functors being adjoined have certain properties. So this moves to the other side, and you get this. Of course, you also have to move sigma to the other side. So it looks very much like there is a monad, and modules over the monad is exactly what are the objects in HHC. Unfortunately, this is not always true, but sometimes it is. Sometimes you can code it all into a monad, and there is a central element sigma in the monad, and so this sigma action is exactly from the central element of the monad. And this happens when C is actually modules over a Hopf algebra. So if you have a Hopf algebra in vector spaces and you consider modules over it, then this whole story works perfectly. This is indeed a monad. It looks like this. And now you see that SAYD contramodules come directly from this, because if you remember the definition of contramodules, they're modules over H, but also there is a map from this to the module itself, which is what I'm advertising here. Okay, so the contramodules aren't weird. They come up naturally if you do this. Of course, then you identify them the comodules, right? Okay, and thus AYD modules. So everything works wonderfully.
May I ask a question?
Yes, yes.
In the case of the Hopf algebra,
Yes.
category of H modules, these okay, so Hopf algebra first of all defines an opmonoidal monad. Don't you want to use this opmonoidal structure?
I'm sorry. A Hopf algebra
Yes.
defines. I see. I don't know what you're saying, so I cannot comment. For me, a Hopf algebra just defines a monoidal structure, and as far as I know, it basically is one-to-one correspondence. So if you have some sort of a monoidal category that satisfies certain nice properties, then it comes from a Hopf algebra. So for me, the monoidal structure captures everything there is. So I don't know what you mean by monoidal structure. But what do we? What
algebra defines an opmonoidal monad on the category of vector spaces, let's say. Now you have only the monoidal category of H modules.
Yes.
So I wonder how this can capture all structure of a Hopf algebra.
Oh no, I mean this is classical.
This is monoidal structure, nothing more.
Okay. Well, yes, of course. You mean that you need some sort of a fiber functor and things like that. I mean, to truly recover H, you need something like that. But actually, for our purposes, remember, coefficients, after all is said and done, is something related to the monoidal category. And in fact, they're quite invariant. So I mentioned some two categories in the beginning, and that via that approach, you can kind of see that if a monoidal category, you can consider its Hochschild homology or cyclic homology. And remember, those will be the coefficients. So for example, if you do it for H modules, you will get yet the Greenfield modules. And then they are invariant under duality, for example. You can replace your monoidal category by a dual one with respect to some module, and they won't change. So what I'm saying is you need very little from the original H, really. The coefficients have to do not with H so much as with the monoidal category that it produces, and not even that.
Okay, thank you.
and no problem. But of course, we can discuss after if the point is I don't understand what you mean, and so it's hard for me to comment. I can only just say more about what I do know, which is what I said. So sorry. Okay, so here, starting with just the monoidal category, forgetting everything else. That's what we're talking about here. But of course, the description of the monad on the category C. So we have C. What to me a monad is just basically like an algebra. It's an algebra, except it's not in the monoidal category. It's in the monoidal category of the endomorphisms of the category. So a monad, you don't even need a monoidal structure on C to have a monad on C, because of course C could just be linear category, and the endomorphisms now are a monoidal category, and an algebra in that monoidal category is what to me is a monad. So that's what it is, and this constructs an endofunctor of C. Now multiplication is highly non-trivial, and that is why sometimes it doesn't really work. But in this case it does, and what I'm saying is that as a functor, at least, this is very recognizable. This is kind of the important ingredient in contramodules. What is a contramodule? It's something where you have a map from this to M, right? And this pops out of the abstract description, which I think is nice. But anyway, that's just motivation. So this recovers the classical description of SAYD contramodules, and therefore modules if you restrict yourself to H finite dimensional. Now, let us talk about bialgebras. And this is the only slide that is about bialgebras. And everything else will be about Hopf algebras in braided categories. Now, the thing is, why I say wrong is because like there's a paper, I don't know, maybe more than one, where people try to do Hopf cyclic homology, not for Hopf, but for bialgebras. And from the very beginning, you can tell that it's not going to work. Why? Because they try to imitate the definition that is the original definition, H module, H comodule. But that relies on this guy being this, right? I mean, if H is finite dimensional, then what is this? H star, and H star modules are essentially H comodules, right? So that's where you get the H comodules. But you don't get that if you apply this theory to a bialgebra. This endofunctor, just as an endofunctor, never mind the multiplication, will not be this. It will be more complicated than this, uglier, less descriptive. But of course, it's possible to write it down. And this isn't even a monad. Like that, as written over here, is not a monad. You cannot define multiplication on it. So, of course, you can get a monad. You do know what this is. It's just not that. And a monadic description is still possible, but it is different because it has to be. Without the antipode, you don't have these nice things simplifying, and certain things aren't isomorphisms, and therefore bad things happen. So in general, what you get is you don't get a monad, you get something that generates a monad. So not any two things can be multiplied, in which case what you do is basically you say it's freely generated by this thing, modular relations. And this, in a particular case, this is a description. So if you have a monoid and you consider the monoidal category as a result, which is monoid graded vector spaces, then this thing is the representations of a groupoid, but it is this weirdly defined groupoid where you say, okay, I know what my objects are. They're just elements of M. So far, this is just like if M was a group. But then you say that an arrow is a pair of elements in M. And where does it go from and to? It goes from this to this. And composition is freely generated by these arrows subject to this relation. And sigma action is x comma 1, which notice does go from x to x, because x times 1 is equal to 1 times x is equal to x. Now, if M is a group, this recovers what everybody knows, right? If M is a group, then you consider a group graded vector spaces. This is a perfectly nice monoidal category. You can consider its Hochschild homology, or if you prefer anti-Drinfeld modules, which will coincide with the Drinfeld modules in this case. And it will be just, what is it? G graded, G equivariant vector spaces, right? So this is in in all the papers about cyclic homology as an example. What happens when your Hopf algebra is like CG or functions on G? This happens, but this is different and behaves wildly different, actually. So I've worked out a few examples, but it would be fun to work out more. If M is not a group, behavior is completely wild. If M is a group, everything's nice. Yet-Reinfeld module is the same as anti-Yet-Reinfeld modules, and it's so very nice. For example, if it's abelian, then the adjoint action is trivial, and so basically you just have a product of two things, G-graded vector spaces times G hat, Pontryagin dual-graded vector spaces. Everything is nice. Not the case here. If M is abelian, but a monoid, it's just wild. It changes from X to X what the stabilizers are. And there is absolutely no relationship between AYD and YD in this case. So it's very instructive to consider M a monoid and use this definition, and then you see that weird things happen. So that is the first indication that maybe you should not try to imitate the definition. You should just try to unravel what these things say in a particular case. So, anything about bialgebras before we move on and never come back to them?
So this was your remark at the beginning, right? That you can have AYD and YD for bialgebras,
Yes.
but they're completely unrelated.
Yeah, and you don't need to like search like that person. What's his name?
Yeah.
Selbig or something. He in his thesis, I mean, he had to work really hard. But you don't have to work hard. It's like, I think you'd have to work really hard to find a monoid that's not a group that will give you two things that are the same. It's just no, they're not the same. They're wildly different. And individually wild. Actually, the center is not so wild. Remember, YD is the center, and AYD is really the Hochschild homology of the category. So we move on. Now, I like more, of course, rigid braided categories and Hopf algebras in them because there's just so much more that you can do. In bialgebras, it's fun project maybe for like a undergraduate or something to work out all the weird things you get, but this is more interesting. So again, if we have a rigid braided category, we can consider Hopf algebra in it. Of course, you can consider Hopf algebra in a braided category, but rigidity is, remember, rigid means inverses, and inverses are good because you don't have inverses, the behavior is wild. Most of the things I say here, I'm not sure they even work if it's not rigid. Like somehow the antipode, who would have thought, is so important, you know? Like first, when you learn about bialgebras, it's bad enough, right? You have multiplication, co-multiplication, and you kind of don't even think about antipode. You're like, oh, well, it's just some extra wrinkle that we don't need to worry about. But it turns out the behavior is drastically different. But so rigid is kind of like that. So the category of H modules in B, not in vector spaces, but in B, that is going to be a monoidal category. And so from now on, that's the monoidal category we will concern ourselves with. But what do we do? Like people talk about Hopf cyclic homology for Hopf algebras in braided categories. And then what do? Again, they try to imitate the construction that is classical. Modules, comodules, and compatibility conditions. And again, this cannot work by this, but it does work sometimes by accident, because we'll see. So we can apply the general construction to this monoidal category. We can do that. And in fact, this is the right thing to do, I think. There are examples we will see later where you have a Hopf algebra and that gives you a monoidal category, but this monoidal category can also be obtained from a Hopf algebra in a braided category. And so even though you might want to have some understanding of anti-Yet-Reinfeld modules for a Hopf algebra, it still pays to pay attention to this, because this gives you deeper understanding, because there is a B, right? B kind of localizes the situation. If there is a B, of course, some Hopf algebras are just Hopf algebras, and you can't replace them like this, or rather they're monoidal categories. But in cases where you can, it pays a dividend. So again, while we might be interested in coefficients associated to this monoidal category, in which case we should not proceed any further. We're done. Then actually, no, we're not done. We are done in principle, but remember, we want to have a computational approach. We want to feel it, and that approach will still be helpful. But it pays to remember B, because, well, we'll see. It really is helpful. And another approach is to imitate the diagram one gets in general. Remember, there were diagrams in the beginning of categories. So let's write down that diagram, but usually the diagram, if B was vec, so you wouldn't even write it, then this would be a diagram of categories, and from that, from its limit, you would obtain the Hochschild homology or cyclic homology of the monoidal category of H modules, and that would be your anti-Eder-Reinfeld modules or stable anti-Eder-Reinfeld modules. But here, what we do is we take H just before, and we just say, oh, well, why not replace B? Why not replace vector spaces by B? And try to do that, right? And see what you get. Now, from size considerations, it's obvious you do not get the same thing from 1 and 2. From 1, you get something much bigger than what you get from 2. And jumping ahead, you cannot even do 2. So, but even if you could, still you would not. The interesting thing is that you can do 2 if you want to do not the anti-center but the center. If you do the center, you can actually do 2 all the time, and it will give you something, but it won't be the full thing. So we will combine the 2 approaches. We will see how, using what you can do, this you cannot. You can gain a lot of insight into 1, which is really what you do have and want to understand. So what is the problem? Like, everything usually boils down to some problem, and this is the problem in this case. Whenever you have 2 algebras, then the monoidal category will allow you to do this, but they will just be objects in the category. They will not be algebras. But when you have a braided category, you can tensor algebras and get another algebra, right?
Mm-hmm.
It's just true. But what is not true is you do not have this flip. Remember how I said this sigma, it says, oh, you have 2 H structures? Oh, no problem, just reverse them. And now you have a new module over H squared. Well, you cannot do that here. You cannot do that in the braided category because you don't have that isomorphism. You have a natural isomorphism between AB and BA. It's just that it's not an isomorphism of algebras. If it is symmetric, it is, which is why in a symmetric case, everything can work. But in general, you don't have this. In general, you have this, where this is tau inverse, and this is tau, which is useless. This is useless. Yeah, you have it, but it's useless. So this prevents a definition of a functor from AB to BA modules. And this is basically equivalent to the tau. Remember how you need a tau, you need to move the last one to the first one. And to have the tau, you need to have this. You do not have this, then it's over. You cannot do anything. So now the question is, what do you need to do? And it turns out, after a long sequence of simplifications, because of course the first idea is rarely the best, and neither is the second, the third, or the fourth, but in the end, the idea is that you need not B. B will not work. Sometimes not at all, other times not canonically. So it turns out that there are examples where just no, B will just not work. Other examples where B will work, but with lots of structures. So what we need the notion of a braided B module, which actually is a known notion. And there are papers about it, and it's related to very many things. And for an unsurprising reason, in retrospect, this is very helpful here. And this is the simplest approach. Like, there are other approaches to understanding what it is that you need. B doesn't work, but what works, right? And there are lots of ways to see it. And this is my latest, and I think it is the best. I think I'll stick with it. So you need a braided B module, right? And additionally, why is it good? Because it's an off-the-shelf component, right? It's something that people know and love and use and understand. You need a braided B module. Now, what is a braided B module? It's whatever is in that box, right? You just have this extra data. You have an action of B on M, but of course, B acts on itself by left multiplication. But you see that B normally doesn't have this extra data of a natural isomorphism of the action functor that satisfy these conditions. Okay? For example, you could try to give this B the identity, but then you would need tau squared to be identity, which means you would need your braided category to be symmetric. But it's not symmetric, then you're out of luck, and this is actually something extra. What does that remind you of? It should remind you of coefficients. Just like in Cyclic, you need coefficients, so too, in this situation, you need coefficients. You need M. M is your coefficient. There is no theory without M, and M is your coefficient. And in certain situations, M can be trivial, but on others it cannot. And in general, you need it. Of course, one always exists, we will see. Anyhow, why is this M good? Because with these properties, this wonderful functor does exist and is very natural. That you can flip. You have an AB module, you can turn it into a BA module, and therefore you can have tau, and therefore you can have this, and therefore you can have the limit, and then everything works. Okay. Of course, to obtain a diagram over lambda, not delta. Remember, delta was the simplices here. We need more. We don't need just a braided M. We need a slight modification of that with what I would call a stable braided module. And it has this sigma such that it factorizes, so to speak, this E. So of course, if you fix an E, there might not be a sigma. And if there is a sigma, there might be multiple sigmas. But of course, definitely a sigma determines E. And actually, the interesting thing is if your E comes from a sigma, then the second condition is automatic. The first condition is still a condition, though. And I just can't find no elegant way of writing in terms of sigma, so I just keep it like this. The condition is in terms of E, but E is in terms of sigma. Okay, so we can define this. Why not? We have now a diagram over this guy. We can define its inverse limit, and that will be our definition of the cyclic homology of this monoidal category, but sort of relative to M. Without this M, there is nothing. But I can remove M and then just have the usual cyclic homology of monoidal category of H modules in B. But with M, it is a different animal, and it is this limit of this guy here using this map, which uses E. So in principle, if you have even the same M, it could have a different E, and then you would just have a different thing here, even though it might look the same. So really, I should probably write like M, comma, E, because it does depend on E, but okay.
So the result is an object of the category. Right?
And no, the result is a category. This is a category.
No,
Which
I
is
mean,
Sorry?
that's the result of cyclic homology of a category is a category again?
Yes, yes, yes.
Oh, that's beautiful.
But it is the category of coefficients, right?
Yes, yes, yes.
You want to find the category of coefficients. For what? For cyclic homology. How do you do it? You take cyclic homology. It is very cyclical. No?
Yeah. So if you have an infinity category, will you get an infinity category?
I'm sure, but I'm not an expert in infinity stuff, which prevents me from answering your question for sure. But of course, the way if you use general enough words, as I believe I have, then people who know can just say yes. All those words have meaning in the infinity sense, in which case, of course, they give you definitions in the infinity sense.
Well, it might be worthwhile pursuing that. I mean,
Yeah, but in this talk, I'm advocating simplicity, hands-on approach. You know.
yeah.
I want cell homology, not singular homology.
Well, yeah, that's
just
fine. Yeah.
but because, I mean, there are explicit computations you can make. You can take stuff, actual Hopf algebras and braided categories, and then you can compute stuff and you get actual concrete things, which appeals to me.
Yeah.
Whereas proving general results about infinity categories, I suppose, is also nice, but somehow less satisfying. Okay, so what happens if B is symmetric? Then, as I mentioned, any B module can be given a braided structure via just identity. And of course, it's even stable. But you see, yeah, and of course, you can do it with M equal to B. And therefore, you remember what I said, you cannot do something? Well, you can do it in when B is symmetric because B itself is a braided B module. In fact, stable braided B module with respect to the identity here. But again, this only works if D is symmetric. It does not work if it's not. And what's worse, though, is it gives you something that is just a piece of the whole thing, you know? It's just a small part of the structure. You actually want to understand this. You want to understand the full category of coefficients for this monoidal category, and what you get is a tiny piece, and not usually not the most interesting piece anyway. So you shouldn't stop there, and definitely none of that works if it's not symmetric. Okay, so conceptually, so here it's conjectural. I did not prove this, but I have no doubt that it is true. But from my point of view, it is not even useful because it is very abstract, right? So, but it does, here I want to mention some very interesting things. So if B is braided, these are monoidal categories. This is untrue if they're not, right? If you have a monoidal category, you can do its Hochschild homology and cyclic homology, and you do not get monoidal categories. I think that Piotr mentioned something like that. He said something about affine versus vector space.
Yeah.
There is an action of the center on the Hochschild homology, but there is no monoidal product on the Hochschild homology. Sometimes, if you have an identification between Hochschild homology and the center, for example, if you have this pair involution, right? But the product that you transfer is bad. It's bad because it does not preserve the stable ones. Using that bad product, you multiply two stable ones, you get something unstable. So in fact, it does not induce for you a monoidal product on the stable ones, which, remember, are the really interesting ones. Like in the business of people who study centers of categories, they think centers are wonderful, right? But we think that cyclic homology is wonderful, right? And
Yes.
so, but it's important to remember that center is sometimes identified with Hochschild homology, but it is not at all identified with cyclic homology. Stable anti-Adrian-Field modules are not anti-Adrian-Field modules. It's the anti-Adrian-Field modules that are similar to the center. But we actually want the stable ones, or at least in that direction. Actually, you should probably consider more infinity type things related to that, but let's not talk about that. So, but when B is braided, they do have monoidal structures, correct monoidal structures, intrinsic monoidal structures. And in fact, you can have a monoidal category with more than one monoidal structure, in which case, of course, since this depends on the monoidal structure, it won't change, but the product will. The product encodes the braiding. And it's different from the braided product on the center. And it is actually known. It is a known product, and it's known in factorization homology as the analyzed stacking product. And the other one is known as the Pence product. Okay, but I actually have managed to derive this product from completely backwards, before I knew it was available, from just what I needed to have cyclic homology. Okay, and so it's completely possible to do it by hand, and very explicitly, and not very beautifully though, but elementary. So there is this product, and it is a very interesting product and worth investigating. But you know, that's not the route we take, but I will mention it on this slide. So of course, this is a right module over this is a monoidal category, and this any braided B module yields a left module over HHB. In fact, it's an if and only if. In fact, braided B modules over M are the same as left modules over this monoidal category. And this, and therefore you can write this, and this is what we conjecture to be the case. So this thing that is defined through a limit, the cyclic homology that's defined through a limit of this category, once you choose an M, is simply the full thing tensored over HCB with M, well, the fixed, the stable elements of M. Now, why I don't like this is because this is very conceptual, very beautiful, but like if you want to compute it, not super helpful, right? Like what is this tensor product over a category? That's not a simple thing, not simple thing. Even if there wasn't even HCB here, it would still not be a simple thing. But once you put HCB there, it's even worse. And also, you don't even know this, right? You want to study these to help you with this. But I will point out that this conceptual conjecture does help you with one thing. What do you think happens when, like I said here, that a B module that is braided is the same thing as a left module over HHB, but HHB is a monoidal category. It has itself as its module, right? And therefore, there is a canonical braided B module, namely HHB. And what happens when you plug in that HHB here? Then you get HHHB mod. So if you replace M by this canonical HHB, then you actually recover the full Hochschild homology. I wrote cyclic here, but it's the same Hochschild homology of HB mod. And this is very good, because that statement is not just words, empty words. It has computational power, because this thing is harder to compute than this thing with coefficients in HHB. So there, now we were getting somewhere. If we follow the logic limit monad classical description, this is what we get. An explicit description of HHM HB mod. In the case where it is just a braided module, you only get this part. When it is also stable, you also get this part. And therefore you can have HC, not just HH. But you see, it's very explicit. It is what I promised. It is an H module, H co-module. Okay, it's not H co-module here. It is a module over star H. So this is not the right dual of H. This is left dual of H. In a rigid category, you have duals on either side. This is that other side. And the actions are compatible in the sense of this picture. And notice here we have the braiding. It plays an important part. Here we have crossings, of course, crossings because we have braided category. And here we have an S right there in the circle. We have an S, the antipode. So everything's used. Now nothing has gone to waste. Everything is used. And this is exactly, if you write this down, when B is VEC, then you recover the usual compatibility condition, or at least a flavor of it, right? There are lots of them, depending on what you choose, but this recovers for you the usual compatibility condition. But of course, guessing this from that is virtually impossible, because every time you have a crossing, you have to decide what crosses over what. And furthermore, of course, we have this abstract M here, so that's also an extra wrinkle. So do I need to say more about what these pictures mean, or it's okay?
I mean, does it have a meaning in the very classical case where we are dealing with algebras only, or Hopf algebras only?
Yeah. That's what I'm saying. If you take this and interpret it in the category where B is vector spaces, then you'll get the usual compatibility conditions. You get H module, H comodule, and compatibility between the action and coaction.
Oh, okay. So this is a
But my question is, like,
condition. This is a condition we need.
Yeah, this is a compatibility condition. So first, M has to be a module over H. M has to be a co-module over H, or rather a star H module.
Yeah.
And then the actions have to be compatible. So this acting by star H first, then by H, is the same as doing this horrible mess. But notice that now it's H that acts first.
Yeah,
and star
exactly.
H second.
But also at one stage, we should be able to land on the ground and recover usual Hopf cyclic, right?
Yes, but this is landing on the ground. We are on the ground. We are right there on the ground. Except the ground is now higher.
I mean,
so.
this is it's like explaining the condition that's needed. But I mean, the result of the theory would be compatible, would be the same as the old.
Yes. But when you have a general B, then there is no other way to write down the condition.
Yes.
Oh, no, I mean, there is. I could write you half a page of formulas, right?
Yeah.
And of course, when you do in actual computations, you do have to like trace through all of these things in order to derive an actual condition. And I have done that in examples. But like to state the condition, there is no more down-to-earth way to state the condition. This uses the braided structure, the co-multiplication, multiplication, the antipode, and this thing, the braided structure on the module.
Yeah.
It
Thank you.
uses everything. Nothing has gone to waste, really, everything. But this gives you only Hochschild, right? And module with such two actions and the condition gives you an element here.
Yeah.
If you want HC, then you need this guy. And in order to have this guy, you need that. So you need your E to come from sigmas. There are lots of sigmas here. They all have to do with each other, but they're all different. So we kind of keep it separate. There is HH, which doesn't need quite as much, and then there's HC, which needs a bit more. But it's okay. In all important examples, both are true. Okay. Now let's talk about examples of stable braided modules. So this is the one I promised, HHB with the usual sigma. It is an example. But let's begin with this. This is the important one that allows the simplification. If you have a stable braided structure on B itself, it is actually equivalent to an anti-twist on B. So an anti-twist is like, look, tau squared is not identity. If tau squared was identity, it would be symmetric, and you could still have these guys, but what would they be? They would just be monoidal automorphisms of the category. But with this tau squared, what this is look, should remind you of something, right? This is like it's just saying that whenever B has such a sigma where this happens, it's like B is symmetric homologically, right? There is a boundary of something which is your tau squared. Does that make sense? It's like tau squared might not be identity, therefore it is not symmetric, but tau squared is cohomologically trivial. Trivialized by sigma. Of course, the point is there are lots of sigmas that trivialize the same tau. That is the point. There are lots of anti-twists. Once you have one, then any monoidal automorphism of your category gives you another one, and usually there are lots. So B can have a stable braided structure. The point is that there are lots of them, and each one of them will give you a different category according to our method. By the way, do I have until 1:45 or 1:30? Oh, sorry, that's
Well,
my
1:45, so you have 22 minutes left.
Okay. But I don't have to use 22 minutes, right? Nobody's ever said when people finish early.
Well, but we expect the 90 minutes to be filled up, so.
Okay. You paid for 90 minutes, you're getting
Exactly, I pay for 90 minutes, right?
All right. So these things exist in examples, but they don't have to. And when they exist, there is more than one. And I'm saying you should take them all, because you see, the one that would recover for us just the usual Hochschild homology of the monoidal category, which is, after all, what we should be interested in, is obtained from this particular braided module over B. But you always have this embedding. You can sum over all the twists these stable braided structures on B itself, and this embeds into this interesting one, the HHB. Sometimes it's not everything, but there are examples where it is everything, which means that in order to find out what is this Hochschild homology of the monoidal category, you just need to individually compute what I described for every single one of these B's with a twist. And as the twist changes, the category changes. So it gives you a decomposition of the categories of generalized, stable anti-Greenfield modules, and they're parameterized by twists in that case. So a decomposition just pops out. Of course, you need the theorem for it, and this is a theorem. Remember, this theorem would have followed from the conjecture automatically. Why is it bad? It's bad because it wouldn't be down to earth. There wouldn't be a correspondence. Like the way I can prove this is I can say, take an object here, I will construct for you an object of the type I described explicitly, and vice versa. Notice that they're very different things. So here you have an H module in here, and an H comodule in here, and a compatibility condition in here. Here, well, you have what you have. You don't know what you have. You have the Hochschild homology of a monoidal category. So this guy is the classical description, the one that came from this, right? So this admits a classical description. And again, by classical description, I mean as originally defined for anti-Greenfield modules. This guy admits a classical description, and therefore, if I have this, then now this admits a classical description, except that instead of, remember, the definition is what? You have modules and comodules and compatibility. Where are these modules and comodules? They're in vector spaces. That's where the original Hopf algebra was in. Here, that's not the case. Here, the original thing was in B, but the modules and comodules are in HHB. So what are the useful consequences? Well, one is that once HHB is described, and often it is obvious, then we build on that and we have a completely concrete description of the classical flavor for this guy. And another is that when this decomposes, that means that this decomposes, because after all, it's this. And when this decomposes, this obviously decomposes, therefore this decomposes. And so we kind of have a parameterization now of this thing that used to be a single thing. It's just the coefficients for HB modules, but now they are a sum of categories parameterized by, in nice examples, the anti-twists, which are very enumerable. And the interesting thing is that sometimes some of those anti-twists being different do produce for you different pieces of HHB, but they are isomorphic as braided modules, which means that they produce the same pieces of the cyclic homology category, which means that your decomposition can be grouped into packets, as we will see. Okay, there we go. So this is very, very explicit now. We take B, the braided category, to be G-graded vector spaces. Now G is a group. And we have a bicharacter. That bicharacter, it gives you the braiding. Okay, so the braiding is you wanna move two things around. Well, you use the bicharacter. Of course, G has to be an abelian group for this to be a braided category. Otherwise, it has no hope. But when it is an abelian group, it still needs a braiding. Of course, you can take a trivial braiding, but that's not interesting. Let us take a non-trivial braiding. Okay, now we can define omega, which is a symmetrization of the bicharacter. Then this is an anti-twist. All the other anti-twists are parameterized by lambdas, which are elements of the Pontryagin dual, which are, of course, characters of the group. And these are all of them. And then, since we do have as braided modules, these are equal, then the cyclic homology of this monoidal category actually breaks up into little pieces, very computable little pieces. And these pieces are indexed by the Pontryagin dual. But more interestingly than that, you can see which ones of these are the same. So it turns out that, for example, if this character, this bicharacter is such that this bicharacter, the symmetric bicharacter, is now non-degenerate, then they're actually all the same. They're all the same. And so if you were interested in HH, then all of these guys are the same, no matter what your lambda is. Of course, that is not true if this is not, like if it's symmetric, remember, there is symmetric, that's one extreme. Non-degenerate is the very other extreme. And what we have here is that they're all isomorphic if it's non-degenerate, as braided modules, but not as stable braided modules. For stable braided modules, you need this extra condition. So stable in the brackets correspond to whatever's in this bracket. And therefore, if two things are stable isomorphic, then the cyclic homologies are isomorphic. So that's what I'm saying, that these things, they come in packets. They're not all different. This thing breaks up, and it breaks up in such things that some of them are always the same. And this depends on B itself. This has nothing to do with H. These things, of course, depend on H, but the isomorphism of these guys doesn't. And so no matter what H is, these things will always come in packets, same size packets. It's just, of course, what's in the packet will change, but the size of the packet will not. So, for example, we can have a sub-example. Now, very concretely, G is Z mod P. P is a prime, and your bicharacter is just this letter. What is that letter? Xi. Xi. Xi to the ij, and P is an odd prime. By the way, if it's not an odd prime, you can still do this. But let's just say it's an odd prime. And this is a primitive Pth root of 1. Define a very simple Hopf algebra. H is just kx mod x to the p. Degree of x is 1. This is the coproduct. This is the antipode. This is the co-unit. I mean, the product, of course, is defined from this. It is kx mod x to the p. And then you see, this is the Taft algebra, right? People know about the Taft algebras. Taft algebras, fairly simple things, well known. Suppose that you want the Hochschild homology or cyclic homology of the representations of the Taft algebra. In other words, suppose you wanted something very classical, something that in principle can be addressed with just a standard definition, and I think can be. It's just not as illuminating. You have an actual Hopf algebra in vector spaces, the Taft algebra. You can compute its AYD modules, its stable AYD modules. What are they? You can answer these questions. Definition has been around since, you know, Piotr and Masood and other people, they defined them. But now you could say, look, it's actually the same as HB modules, where this is B. Where is B? Is B anywhere? There's no B.
Well, it's on the previous slide, no?
Yeah, it is on the previous slide, but it should probably be
You said
on
it's
the
a
slide.
sub-example, so.
Yes, but still there's no B here. But it is in that B, right? When G is this and Chi is this, and then HB modules is exactly this. That is obvious. But what is interesting is that, you see, this is much simpler algebra, right? Although it is in a braided category, it's much simpler than the Taft algebra. Taft algebra has another generator, and there's a mess of the relations and stuff. Here, nothing. It's just easy. And of course, we can enumerate. What?
No. So I see. So that sort of the beauty of Taft algebras is now hidden not in the algebra H. It's written in this sort of stability S or whatever the letter is.
What is S? There's so many things that could be S.
Yeah. So sorry, I'll just
sigma.
point to it because, sorry, my Greek is a bit rusted. So how do you pronounce this letter?
Oh, this is the sigma.
That's the sigma. Okay.
Yeah, it's slash var sigma.
Okay, so the slash sigma. So
Slash
am I
var
correct
sigma.
in saying that, because this does not look to me like a Taft algebra? I mean, that's very simple. Everything looks commutative, co-commutative. You have some twists typically for Taft algebra by some group like, if I remember correctly. So now, am I right in saying
the group like is hidden in B.
Yeah.
In B, not
in
in
B.
this guy.
Not in
B.
it's in B, not in this. Okay, but it's hidden.
No.
Okay, right.
Yes,
Okay.
no. I mean, this what I'm saying here is true, and people. I mean, I think Majid points it out in one of his books. You know, it's not like a revelation, but it is a nice application, because you see, you could address this classically, but I'm saying you shouldn't. You should really consider it like this, because it's much simpler. H is much simpler than the Taft algebra. As you say, there is no group like. Group like is hidden in B. But then at the same time, HB for B being this is trivial. Everybody knows what it is. you know?
Mhm.
So it really breaks the problem up. instead of being one solid thing with complications, now there is study HHB separately. In this case, it's trivial, and now use H on it, and H is also trivial. And one triviality applied to another triviality trivially yields nice things. For example, this, right? So first I say that I can enumerate all the anti-twists. And therefore, I know exactly what parameterizes the pieces of my cyclic homology. So first of all, Hochschild homologies are all the same, like I said. They all are representations of UQSL2. So we have the small quantum group of SL2 at Q. Q is this. Then all of these guys, as T varies, are these. So therefore, the total thing is just a bunch of copies of this guy, which people know, actually. But now we get it automatically. But the interesting part is what happens when you now pass to C, because now, remember, you are not looking at B sub T as a braided module simply, but as a stable braided module. And as stable braided modules, they're not all isomorphic. There is a single one, which corresponds to T equals to 0. And if you compute its cyclic homology, you get just vector spaces. So it is trivial in a sense. It is a very trivial piece. But then there are the non-trivial pieces, and they come in pairs. For every T not equal to 0, B sub T and B sub minus T is the same, even as stable braided modules. And therefore, the cyclic homology of this guy in here and in here is the same, and is non-trivial. And therefore, the total cyclic homology of the Taft algebra, or other of its modules, in other words, the AYDs, the SAYDs for the Taft algebra decomposes. The category decomposes completely, and there is a separate trivial piece, and then plus, and then there are how many? P minus 1 over 2 non-trivial pieces, but each piece is a pair of identical categories. So they come in packets of 2. And actually, the further interesting thing is that these things, the absolute values of T, the index points of the spectrum of the center of UQSL2, which means that these modules here, right, they themselves localize over a few points, the spectrum. And it turns out that these guys exactly correspond to something sitting at a particular point of the spectrum. It's not exactly what is sitting at a particular point of the spectrum, but it is some sort of a quotient of it. So there is some, it's like there is a central element, and it acts by, of course, a certain number at every point on the spectrum, and it acts by something non-trivial, which means that piece disappears everywhere except at one point where it acts by something nilpotent. And so you have a very non-trivial category sitting at that point. So it's interesting, actually. But the important part is that they always come in pairs. What they are in this particular case where you take the Taft algebra is a separate issue, but they always do come in pairs. So big difference between HH, where they're all the same, and HC, where they're all suddenly different, but they do come in pairs for the T not equal to 0. Okay, now, how much time do I have? I have just one more slide, so I better make it last.
Yeah, 7 minutes.
I better make it last. This is the last slide.
Okay.
Because so far we have not discussed cohomology. We only talked about coefficients. Coefficients. I mean, in principle, we did discuss homology. We said this homology of a monoidal category, and this is what coefficients are. And then we talked about coefficients. But originally, people want to do cohomology of an algebra, right?
Yeah.
We want cohomology of an algebra. So what is it that you get from this? Suppose that you have M in HC M HB mod. Can you get for an algebra in HB mod some sort of a cohomology theory? The answer is, of course, no. Unless, of course, M is HHB, in which case this would be HC HB mod, in which case, by definition, you would get a cohomology theory. But what happens when it's just an arbitrary M? Well, it turns out then you need a little bit more. You need a stable K in M. So you need an actual element of M, which is furthermore stable. In other words, remember M comes with not only the braided structure, but also with this stability automorphism. So every element has an automorphism. You want one where the automorphism is identity. So if you have such a K, then you can actually have a cohomology of A, where A is an algebra in HB mod. How do you do it? Like this, like it says in the box. So what it says in the box actually is a construction of a symmetric contratrace. It's this gadget that where you feed an A to the tensor n plus 1, and you get a cocyclic object. So whenever you have such a gadget, you just take powers of A, feed it into it, and you automatically get a cocyclic object. And I stop there because you see, once you have a cocyclic object, everybody knows how to get cohomology, right?
Mhm.
So I will just stop there. I want to say that I want from an algebra to get a cocyclic object. How do I do it? I feed it into this gadget by taking its tensor powers. Now, this gadget has to have certain properties. It has to be a functor from HB mod to vector spaces, but there are lots of such things. It has to have additional structure. I have to be able to do a flip. I have V, W here, and here I have W, V. I have to be able to go from home from VW into something to home from the WV into something. I have to have this identification. That is the crucial part. That is what allows you to define a cocyclic object. The symmetric part is a technical condition. This is why I need this, but that is not the important part. Okay, somehow structure is more important property. So this demonstrates the structure. So again, there is some notation, right? So what do I mean by this? I mean, given a map in HM mod from a product of this guy and this guy and this guy. Now, this is slight abuse of notation, right? What I mean is V tensor W times K. You see, K is an element in M. V and W are elements in HB mod. I can, of course, multiply them and then act on K, and the result will be as it should be. Well, and so with that bit of notation, I hope the rest is clear. It actually maybe not clear now that I think about it. Like, what does this mean, you think? What does this mean? It means that you have this co-evaluation map that maps identity to star H, tensor H, and H goes and acts on this, and star H goes and acts on this. That's what that means, for example. Of course, this is part of the braided structure. This is part of the braided module structure. This is part of the braided structure. So you're interchanging V and W like this. And notice that one passes under the other. And this again, one passes over the other now. And this is the map. By the way, if you do this in a classical case, you will recover the standard thing. It's just that it looks like this because you have a braided category. All right.
You can see here that stability is crucial, right? I mean, that's
Stability is crucial if you want a cocyclic object as opposed to what they call a paracocyclic object.
Exactly, yes, exactly. Yeah.
So some people are perfectly happy with paracocyclic object. And
maybe a reminder for everybody. So paracocyclic is when tau n to n plus 1 is not identity.
Yeah. And so, and now I will go on a little bit of a rant. So people, when they do this and they're like, oh, we don't have a cocyclic object, we have a paracocyclic object, let us mod out. And then, but that is wrong. I feel that is wrong. It should never be done. In fact, it should be taken as a warning that you did something wrong, and you should try harder to get a cyclic object. Because you see, like you said, if you don't have the sigma, if you don't have stability, then you don't have tau to the n be an identity, and if you don't have it be an identity, then that's not really what you should be doing. The solution isn't to just mod out. The solution is to just go back and see what you did wrong. In this case, if K is stable, then this will work.
I have a very naive and stupid question, if I may. If I would like to replace in this particular place cocyclic by cosimplicitio, how would this look like? Just cosimplicitio.
Well, for that, you need you still need tau to define the final phase, but you no longer need stability, right?
Exactly.
So
Exactly.
it would work, and you don't need stability. You don't, not necessarily, there's two places where you have stability here. You have, go away. There's this thing that's blocking my view. I don't know if it's blocking yours. Okay, there we go. You have stability here. You see the C here, and you have stability here. So both are stable. You need both to be stable for it to be cyclic. However, if you want to do your simplicial business, then everything will work wonderfully. You do not need sigmas anywhere, and you can do HH here, and you can do M here, and there is no sigma to speak of, therefore no C. Everything will still work. Yes.
Yeah.
And I'm free now to go to the next slide, right?
Yes. Okay,
Yes.
thank you so much. You went 15 seconds over time.
But that's probably your fault.
That's perfectly. All right. Okay, so let us now begin with questions. Tomek, I see you.
Yes, I have a question. There's a series of papers by Kaledin,
Yes.
who also considers some general theory of coefficients for cyclic homology, which is mostly based on something which is called trace functor.
Yes.
Would you compare your contra trace?
Yes, it's exactly the same thing. It's exactly the same thing. It's exactly same thing, except up to co-trace, contra trace, just pointing the wrong way, and other than that, is the same thing. Yes.
So your theory is more special?
No. My theory isn't about that. Like, it began. My journey into cyclic homology did begin with studying traces and showing how they produce Hopf cyclic. Like, as far as I know, Kaledin did not do Hopf cyclic. He didn't care. What he wanted was to have coefficients where there shouldn't be any, right? He wanted coefficients in the original setting, where I don't think that from my point of view, there should be any, right? But his notion of trace, and they call it shadow in other papers, other people, like, this is a notion that keeps getting reinvented, like, I guess, the wheel, and but it's all the same. But that is not what I'm talking about. What I'm saying is that as soon as you get what I call a contra trace, he would call a trace, some people would call a shadow, then you have a cyclic theory. And all I just showed you is how to explicitly define a trace, if you want to call it. But I think he did originate it, so let's call it trace. Then you get the theory. But I still want to show how my objects get the trace, and then I claim I'm done. Like, I stop at the trace. I go no further. So basically, I stop where he would begin. I show how to understand the categories of coefficients, how to define categories of coefficients, how to localize categories of coefficients, and various tools for them. And I do explicit computations. I compute categories of coefficients. In some sense, it's like studying D modules without ever studying cohomology, Like, you can have cohomology of a space with the coefficients in a D module, and some people study those. But notice that I did none of that. What I do is concern myself with understanding D modules themselves, as opposed to computing the cohomology. So that so it's completely kind of the overlap is almost trivial between, like, the trace stuff and this. Okay. Although I have some earlier work with Masood and Mohammed Hassanzadeh, which started this, which is exactly showing that using the notion of a trace, you recover Hopf cyclic. But again, this is independent. This is not what is going on in this particular case.
May I ask another?
Oh, yes.
More simple question about t equal to 2 in your example of Taft algebra. What happens then?
It's just so much less, right? So, for example, I'm really happy about packets, right? When things for some reason come in multiples, it's always mysterious. And here, things come in multiples, and there is a very good reason for that. It's just because of what I explained. We do not get that when p is equal to 2. In p is equal to 2, there are only two things. There are only two things, and they're all different. One is trivial and one is not trivial, and together they give you everything. So there aren't packets. There is no symmetry, and it's less satisfying. Also, when p is equal to 2, it's a symmetric category,
Okay.
and which is also something that is bad from my point of view, because I like categories that are not symmetric, because then I can say that, oh, look, this is new, as opposed to not new. I can say that there is something interesting that can happen when p is equal to 2, not a sub-example of what I described, but I did start working that out. It is very fascinating. What you do is this: you take Z mod 2, so that's your group, but you do not consider Z mod 2 graded vector spaces. With the braiding that I described, you would just get super vector spaces, right?
Yes.
Which is a symmetric category. Instead, what you do is you mess up the associator. Instead of being this, in every monoidal category, there is the associator, which I neglected. I said associative in quotation marks because I didn't want to talk about that. But you can have a non-trivial associator even in Z mod 2 graded vector spaces. And this non-trivial associator will allow you to have a different braiding. And that braiding will not be symmetric. In fact, it will be non-degenerate. And what happens then is, I think, more interesting. Unfortunately, you cannot have an analog of Taft algebra, then you have to have kind of a larger thing. But it's interesting. It's interesting that this theory, what I like I drew these pictures of strings intersecting themselves and splitting and joining, and it's very powerful language because it doesn't care about twisted associators. You can still use it and everything still works, except when you're unraveling, you should remember that when you do associations, you should twist it. But other than that, it's still, those beautiful pictures still work even when the associator is twisted. And so you think maybe you should be careful. And yes, you can work it out for p equal to 2 without the twist or with the twist. I'm just saying that without the twist, it's not very interesting. But with the twist, it is very interesting. So you almost wish like there could be a physics, not with like super vector space, not the supersymmetry, but like that other one, where the braiding is non-degenerate, where the associator has been twisted. That would be truly weird physics.
For Swidler's Hopf algebra, this four-dimensional non-commutative, non-commutative, the category of comodules is equivalent to the category of two-graded complexes. So does this homological flavor of the category of comodules have anything to do with the physics you are?
Oh, no, I'm not saying this has anything to do with physics. I mean, if I don't know anything about physics, so unfortunately, I don't
so this
know.
is not about SUSY, nothing like this. Okay.
No, nothing. I'm just saying, like for someone who doesn't know any physics, it is very interesting to think about how you could just, do this instead. See if you could, just because.
So I categorically deny any involvement with physics.
I deny any responsibility for physics, but I would like to think about what this could mean for it, because, like, again, this thing where things come in multiples, that's also very suggestive,
Okay. Thank you very much.
Okay.
Anybody else? Any comments or further questions? Masood, Adam, whoever.
So what's coming next?
Next,
Yeah.
I mean, honestly,
It's not a fair question, I know.
I want to write up these things because I have a lot of notes and have finished things in various stages of being written. But actually, if I were to say like where to go from here, I would just honestly study bialgebras. It's just fascinating to me how badly they behave and how different they are than Hopf algebras. And this badness is not necessarily a bad thing. I think it's good.
Well, I mean, has cohomology of groupoids been studied intensively? I mean,
But that's the thing, right? It's not groupoids. It's not
no, not
groups.
groupoids. Sorry, semigroups or monoids. I mean,
Yeah, I don't know. I mean, I
uh,
don't know. I don't know. I mean, monoids, they are important. The computer
very
scientists love
important.
them.
But has there been any kind of successful cohomology theory for them? I mean,
Well, I mean, what we have here is a braided category coming from a monoid, right? And no, sorry, not braided. I am confused. There's no braiding here. Although you could, yeah, you could, but
no, I
that would
mean,
be
my point is that Hopf-Cyclic is an extension of group cohomology and Lie algebra cohomology. So for
yes,
bialgebras would be extension of monoid. I mean, yeah,
yes,
semigroups cohomology, which is not
yes.
distinct theory in a way. So maybe I don't know. I mean,
No, I was thinking more like if you have some sort of a monoid and you have monoid graded vector spaces, then you want to study its Hochschild homology or cyclic homology. Now that I know how to do it and I get these weird answers, what do they mean? I don't know what they mean. Maybe
right.
that's what you're also asking, if anybody even cares, but surely, like what you said, right? People care about group cohomology, right?
Yeah,
And group
a
cohomology
lot.
and group cohomology has something to do with Hopf-Cyclic, right?
Oh, absolutely.
Yes,
But
and so by extension, since now you have it for monoids, then now you should have something for monoids. And the question is, shouldn't there be something useful about monoid cohomology? I don't know. Maybe it's too wild. I don't know.
it's a reverse now development. So you start from bialgebra and you land
Yeah,
in monoid cohomology. That's anti-historical. Yeah.
but what is amusing is just how bad it is. Like all the things that you have to work so hard to find a counterexample for in Hopf algebras, here they come for free because it's just that badness is regular. It's just what happens normally.
Yeah.
And yeah, but for braided stuff, I think that it's more promising. But again, it's related to bialgebras. What happens when you drop rigid? Like what happens when you drop rigid? Everything I do requires rigid, but in principle it shouldn't, you would think. Like, can you drop rigid? Yeah, the results might be uglier, but like, can at least the definitions make sense? I don't know. So you could try dropping rigidity from the braided category. It
If I
could be
understand
interesting.
correctly, rigidity is some sort of finite dimensionality condition. Is that?
Well, that's what I thought, but I no longer think that. I think if it has to do with finite dimensionality, then that is easily rectifiable. For example, it's rectifiable with contramodules. Modules are
Yeah.
fixed up with contramodules, and the problem is solved. They aren't that different. They aren't significantly different.
Yeah.
Whereas you sometimes have non-rigidity in a much stronger sense. You have non-rigidity because you don't have inverses. So for me, non-rigidity now is lack of inverses, because that is unfixable. You can consider finite dimensional vector spaces graded by a monoid, and that is not rigid, even though they're all finite dimensional.
Right. Okay, very good. Thank you.
Okay, if there are no other questions or comments, let me close with a little historical remark. I cannot resist it because you mentioned Taft Hopf algebras. And Taft Hopf algebras were used as examples in a very beautiful paper by Kaufman and Radford, which actually introduced module pairs in evolution 5 years before Kohn and Moscovici. And for me, this was absolutely amazing. And even conventions were identical. It wasn't that two concepts were equivalent, they're just identical. And they did it in order to study not foliations like Kohn and Moscovici, but topology of knots. And they came about as some square roots in this Radford's theory of S4. So this is very fascinating. I mean, these module pairs in evolutions, which now we think about as one-dimensional stable heterogeneous modules, actually were born 5 years earlier than we expected. Yeah, and I have this recollection because when Kaufman and Redford were doing examples and counterexamples, they precisely used Taft algebras. So that's just a historical remark. And Masoud, by the way, don't you think it's nice when somebody refers to our work as classical?
That's very nice. Yeah.
I'm sorry, I did not mean to offend.
Yes. Thank you so much. So let's thank Ilya again for the very nice talk. Thank you so much. Now let me stop recording.